Okay, welcome back everybody to data analysis. Today we have a neat lecture on binary and categorical predictors. So this is going to be pretty short by way of theoretical content. I'm going to do a more in-depth R example so we can see it working. But this is just a way to use qualitative or categorical predictors in your linear regression models. So in the last lectures, we looked at multiple linear regression. I hope you sort of had an impression from that lecture that linear regression is more powerful than sticking a line through a bunch of points, right? When we do things like transformations, we can put non-linear transformations of the inputs into linear models, right? And so the big takeaway there is that the linearity occurs in the beta terms, not necessarily in the input terms. So today we're going to talk about binary and categorical predictors, which sort of just give us another direction which we can look for building linear models and add some more subtlety to the types of models we can make. There's a lot of different ways to describe this. We'll call it binary predictors, categorical predictors, qualitative predictors. In the machine learning community, they call this one-hot encoding. But it has a lot of different names, and I think that once you see it, it's a pretty straightforward concept, and seeing it described with different vocabulary words, I hope will be clear. So here are the sections in the references. So let's just start with an example. Okay, so this is kind of quaint, but so what we want to do is we want to build a linear model for IQ of MPS students using a qualitative predictor of whether the student is in the OR curriculum. Okay, and I'll just say here, I know I have a lot of students joining this class from the math department. Okay, so don't mean to roast on any math students here, but this is just a home team kind of question. So the response variable is going to be y. This is right quantitative. It's IQ, intelligence quotient. So okay, we're doing regression because we have a quantitative y. And then the predictor is the student in the OR curriculum. This is our predictor x. We have a single predictor x, and then I'm going to define the predictor to be 1 if the student is in the OR curriculum and 0 if not. Okay, so I'm saying, okay, I'm going to turn this, is the student in OR into zeros and ones. Okay. What that allows me to do is that allows me to build a linear model as follows. So this is sort of our true relationship between the variables x and y, right? And then we have an estimate where we estimate our beta 0 coefficients and our beta 1 coefficients, okay? So just to be clear here, of course, I'm using scalar notation just to be extra simple in this case. I hope by now you're sort of increasingly familiar with the matrix notation. Here we're using scalar. And so what's actually happening here, right? So what this is saying, so this is our estimate. Let's look at what our estimate does. So if the student is in OR, okay, that means that x is going to be 1, right? And if x is 1, then that means that our estimate is going to be beta 0 plus beta 1, or beta 0 hat plus beta 1 hat times 1. So the estimate of the IQ is beta 0 plus beta 1 hat, right? Whereas if the student is not an OR, then x is 0. And so our estimate is just beta 0. So what you can think of this beta 1 hat term is an adjustment to the intercept with the knowledge that the student is, for example, here in the OR curriculum. Okay, so we're basically just building a way to modify our estimate of the intercept term with this binary predictor, which says, adjust the intercept knowing that the student is in a certain category. Okay? So what are the interpretations of beta 0 and beta naught? So this is what I just described on the previous slide, but just with a little more detail. And so this is our estimate. This is y given that the student is not an OR. So our estimate of this is beta hat 0. Okay? So this is so what I've written here is the estimate of y, given that the student is not an OR, is obviously the estimate of y given that x equals 0. This is sort of the equivalent condition that I've I use to define x. And so again, the beta 1 term vanishes, and we just get beta hat 0. And similarly for when x is equal to 1. So okay, so my little punchline here, we hope that this adjustment is positive, right? So this is knowing that the student is in OR, we have this adjustment, we have this estimate beta hat 0. Excuse me, knowing that the student is not in OR, we have this estimate beta hat 0. Know the student is in the OR curriculum, beta hat 0 plus beta 1. And so we hope that this estimate, or this beta 1 hat piece, is positive, right? What this would be saying is that knowing that the student is in the OR curriculum leads us to adjust our estimate by a positive amount, adjust our estimate of the IQ, that is. Okay, so ha ha ha. All right, so in general, we can code categories as using these indicator or dummy variables x. So as we saw in the previous example, what I did is I took a category, right? There was 2 categories to consider in the OR curriculum, not in the OR curriculum, and I defined a predictor, 0s and 1s, based on whether or not basically just denoting membership in the category, right? So 1 denotes membership in the category, 0 denotes membership in the complementary category. So yeah, so just some vocabulary words here which I've highlighted. We call this encoding, or encoding a categorical as a binary predictor, and we can call these x binary predictors. We can call them dummy variables. We can call them indicator variables. Again, there's a lot of equivalent vocabulary to describe what's going on here. Okay, so there's two categories here. Of course, there's for category C, we have membership in the category and the complementary category, which we're not in this category C. And so what we refer to this x equals 0 category as the reference category. Okay, the reference category, what it does is our prediction y hat is equal to beta hat 0. This is our reference category when we set the predictor equal to 0. Okay, and then our estimate is just equal to our estimate of the beta hat term. Okay, so there's the other category, which is x equals 1, but this is just another vocabulary word. Reference category is when the dummy variable, the indicator variable, the binary variable is set equal to 0. Okay, the beta hat terms, so associated with the indicator variables, which are so right. Let me describe this. This is a little sparse, but so we have this reference category, which corresponds to this beta hat 0, and then the coefficients of these indicator variables, right? So that is all of the this is another way to say this is that beta I for I not equal to 0. Okay, because the beta 0, it's not a coefficient of an indicator variable, right? An indicator variable is one of these x things, so all the other coefficients will be attached to indicator variables. One of them will not. That's beta 0. So all of the betas which are not equal to 0, the ones that are attached to indicator variables, are called contrasts. Okay, so we have a reference category associated with beta equals 0. We have contrasts, which are the coefficients associated with the other variables. Okay, and so here's a quick question. What if we had swapped the roles of the reference categories? Okay, so what that means is that x equals 1 when the observation is not in C. So here I've said, here's a category, and then I've said x equals 1 when you're in the category, x equals 0 when you're not in the category, right? So what if I had swapped their roles and said x equals 0 when you're in the category, x equals 1 when you're not in the category? Well, intuitively, if we think through it, we shouldn't change our actual predictions, right? We should still be able to say, well, if you belong in the category, feed it through this machinery, whatever you're going to do, you should predict the same number. If this encoding affects your predictions, sort of it seems sensitive to a choice which it shouldn't be sensitive to, right? That is, your prediction depends on how you code the category. And so, well, it turns out that actually it's not sensitive to this flip. And so if we do swap the roles, you can sort of think about it yourself. But what happens is that the beta naught term actually becomes beta naught plus beta 1, and the beta 1 term becomes negative beta 1. Okay, so this is sort of just saying this is the old in the previous encoding, and this is the new, and this is the old and the new. Okay, so what will happen if we do this swap, right? So then x equals 0 would correspond to being in the category, and so what would happen is your new intercept would be beta 0 plus beta 1, and then you would subtract off the adjustment in order to get back to what you originally had. So the actual encoding itself doesn't change the predictions. It's a little more intuitive to have x equals 1 denoting membership in a category, but you can sort of rest assured that if you were to swap them and say, you know, for example, in this OR example, if you would say define the predictor, is the student in a curriculum besides OR, right? Then, and just proceed, you know, defining 1 in the category, 0 if not, your actual predictions at the end of the day would still give you the same numbers. Okay, and here when I say the student is not an OR, of course I'm dealing with the complementary category instead of the student being an OR category. All right. So, okay, so that is the single category description. So we have a category, we have its complementary category, and so what if we have multiple categories? Okay, so we call the different categories levels. This is another way to describe it. And so we basically hack the same kind of technique we've been doing, where we're just encoding categories into this situation where we have multiple categories. So if we have k levels, that is k different categories, okay, you pick one level as the reference level. That is the prediction which corresponds to beta naught hat, okay, and then you introduce k minus 1 indicator variables for the other levels. Okay, the k minus 1 indicator levels, these are just different x's, right, for the different remaining levels. So what you say is all of the other categories besides the reference category are going to get their own predictor, that is, are you in the category or not, okay? And then you get a contrast, that is a coefficient, a beta term, for each of those indicator variables, okay? And so again, each contrast is adjusting the intercept from the reference category to the level which has been coded in that indicator variable. Okay, so same idea, but you get introducing k minus 1 indicator variables for the different categories instead of just 1 indicator variables for the other categories. So here's an example. So same idea, we're going to build a linear model for IQ of MPS students using students' curriculum as a predictor. Okay, and so we have a Y quantitative output, and then instead of a single single category, which is a student in OR, we're going to have 1, 2, 3, 4, 5 categories here. Okay, so we have 5 categories. That's this X categorical predictor. So we want to encode it using these binary predictors. So what we're going to do is we're going to choose a reference category, just as I talked about in the previous slide. And so I'm going to choose my reference category as other. So that is curriculums, any curriculum not corresponding to these 4. Okay. So, and this corresponds, of course, to, as I described, just the intercept term beta 0. So that is all the binary predictors have been set equal to 0. So then I'm going to have I'm going to assign new predictors, which is going to be this first one is going to be a 1 if a student is in OR and a 0 if not. The second one is going to be 1 if a student is in physics, 0 if not, and so on and so forth. Okay. So what I'm doing is, of course, have these 5 predictors, choosing 1 as a reference, and the other 4 I'm assigning to their own predictors, each of which get their own contrast. Okay, so for example, the contrast, the coefficient that's attached to x4 here, would say, how do I adjust my prediction with the knowledge that the student is in an engineering curriculum? Okay, and so and it's important to keep in mind that when I say adjust, I mean adjust from the reference category. How do I adjust my prediction for the other curriculum if I knew that the student was in an engineering curriculum? Yeah, so another bit of language. You could say contrast. You can also say the adjusted effect. So the contrast is the adjusted effect of category I on beta 0. Okay, so that is what's the adjusted effect of the engineering curriculum on the other curriculum. Okay. So again, so again, there's a lot of vocabulary sort of being thrown around here, right? Contrast, adjusted effect, reference category, all these sort of things. But I actually find that these, it's not always this way in statistics, but this language pretty much describe what's going on in a good way, right? So when you say adjusted effect, you're like, okay, you're adjusting. It's what's the effect of engineering, right? But it's not just the effect of engineering. It's relative to the other curriculum. That's what this contrast is. So when you say adjusted effect, it's clear that it's the effect, right? But not just the effect. You're adjusting it relative to the reference category. So even though there's a lot of vocabulary words going around, I find that it's well chosen for what's actually going on. Okay, so so this is just continuing our previous example. So we were predicting IQ from a student's curriculum, and we had the reference category correspond to the other curriculum, and then we had OR, physics, engineering, and I think applied math. And so it's important to note here that even though these xi's are binary variables, it doesn't change anything about how we actually solve for our least squares estimator, how we solve for the optimal beta hats, right? We just have predictors. We get to feed them into a design matrix. We get to take x transpose x inverse, x transpose y, and we can solve for beta hat exactly as before. Okay. The only thing that I want to point out that's a little weird is that plots get a little odd in the sense that if you're going to plot something, for example, your residuals, your y's, I'm not sure, against your predictors, right? Scatter plots are not appropriate anymore because you have binary variables here, and so scatter plots don't really show you a lot, and it's better to replace these scatter plots by group box plots, where you sort of have right, you would have something that looks like this, right? You would have x 0, 1, and then put a box plot here for all the observations corresponding to x equals 0. And a box plot here for everything corresponding to x equals 1. This will tell you more information than the scatter plot will because of the structure of these x variables. But besides that, everything works as we've already discussed in the previous lectures. So yeah, so in particular, this is still our least squares estimate. Okay, and in general, you can have a mix of categorical and numeric predictors. Okay, so if you have a categorical predictor, you can encode it as these binary or indicator variables, right? And you can keep your numeric predictors as you have them and just continue to use them, right? So I don't know, we could add another predictor here in this IQ problem which we've been discussing, and say we could say a second predictor which is not just the student's curriculum but the student's age, for example. And say we could have age, curriculum, just keep age as we usually would. It's quantitative, it has a slope attached to it, some beta, and then encode the categorical predictor as in this binary format. Okay, so the big takeaway is that with this technique, we can predict quantitative variables, right? This is the regression part, using categorical and quantitative variables. Up until now, we focused only on the quantitative part. You can use quantitative variables as predictors by coding them as binary predictors. Okay, so linear regression is now able to take these categorical predictors as inputs for us. Okay, how do we do this in R? As I mentioned, I'm going to do an in-depth R example. You can use as.factor to code a variable as factors. So that is, you take categories and you want to code them in a way that R will understand them as binary predictors. You can do this with as.factor. Oftentimes R will do this by default when you load a data frame, but in some cases it will load it as character strings, and you can use as.factor to code it as factors explicitly. Another helpful command is this relevel command. So relevel will set a reference category. By default, if you use as.factor, R will just pick a reference category. But if you want to have a certain reference category, for example, in the IQ example, we were using other as a reference category, and we were interpreting our contrasts relative to the reference category, which was other curriculums. You can have R do that explicitly by using this command. So this is a vector x, this is a factor vector x, okay, and you're giving it one of the categories as a reference category. All right, everybody, and sorry for the quick hiccup in the video. I was recording and my cat decided to make an appearance, so I kicked him out, and I'm going to finish the tutorial here. So where we're picking up is we just introduced how to do categorical predictors, doing binary encoding, and so I'm going to do an R tutorial, and this is going to be more in-depth R tutorial with an eye towards looking through transformations, good transformations generally, but also including a portion on binary predictors. So if I switch over to R here, so the example that I'm going to work through is combining a couple of different CSV files. So I got personally interested in this question. Two things which we hear a lot about sort of in the news and maybe just where I'm from in California, but we talk a lot about homelessness rates, and we also talk a lot about incarceration rates. Okay, and so I'm interested to see, is there any relationship between the two of them? In particular, I want to know, do incarceration rates, is that effective predictor of homelessness rates? And in particular, I'm going to also use this geographic region as a predictor. So can we predict homelessness using incarceration rates and geographic region? I'm going to build a few linear models, and what I want to know is this incarceration rate useful as a predictor? Okay, so I have a couple of this. So a lot of this code is just sort of messy and data cleaning. So what I'm going to do here is I have a CSV for each of the variable I'm interested in. So I have homelessness by state. I have population by state. That allows me to turn these counts of homeless and incarcerated into rates. And I also have this helper data frame, which is the abbreviations for each of the states. And the reason for that is that some of the CSVs code their states as the abbreviations, like, you know, California is CA, and some of them just write out the full state. And so with this data frame, I can link the two of them. Okay, so I'll just go through and run all these commands, and then what I do is I'm basically extracting the variable of interest from the data frames, and this for loop is basically just seeing, you know, if a state name is in this abbreviation CSV and its abbreviation is in this abbreviation CSV, then I should include it in this data frame that I'm building. So I just go loop through and populate the data frame. I'm populating the population, prison, and homelessness numbers. This is something you actually might see in your day-to-day practice, which is removing commas and numbers. Sometimes people put commas and numbers to increase its readability for really large numbers, but if you do that, R will try and treat that as a string and not a number. And so this gsub command, what I'm doing is I'm replacing all of the commas with just erasing them by substituting out this comma with sort of this blank string here, this empty string.
I do that, and then I have a data frame which has, if I can pull up its column names really quick. So here's the summary. I have states 51. This is because I have Washington, D.C. in there. Abbreviations, population numbers, prison numbers, and homelessness numbers for each state. And if you have interest, these are hosted on my website, and like I said, I'll post the R code. There's different attributes. So, for example, the homeless CSV has different attributes about, for example, children who are homeless, different categories based on the demographics of the individuals. Same thing for the prison data set, but I'm just using the total numbers here. Okay. One thing I will note is that there's an NA, so the District of Columbia did not report its incarceration numbers, so I just remove it. So now the data frame has exactly 50 states. DC is not included. I'm going to take some log transformations of some of these numbers, and this just comes from previous experience, but this is good insight. This is nothing that's required mathematically, but let me just show you this. For example, the population numbers. So here's a histogram of the population numbers, and we see that there's this large right tail, right? And this large right tail, for states like California and Texas and New York, which have extremely large populations relative to most of the states. Actually, this makes the population predictor, it's kind of problematic, because what's going to happen is you're going to try and predict in these regions. Most of the data is in this region, but in some of the data is extremely large, and so if you can sort of imagine trying to fit a line through a bunch of points where most of them are in a certain region, but a few of them are very large, it's sort of prone to some errors. And in particular, the influence of these points tends to be really high. So you have a few very high influence points and a lot of very low influence points. And so what's often useful is to try and transform the variable so that you get rid of this strong right skew. Okay, and so the idea is you want to transform, if you can, to make a predictor look more Gaussian, look more like symmetric, and this just kind of reduces those problems of the high influence. So I'm going to take some log transformations of some of these variables. When I do take that log transformation, I'll take this histogram from something that looks like what we see to something that looks like this, right? So this is much more. The tails are much less problematic. Okay. So again, here, then what we're doing is we're interpreting these numbers. So as population, this is 10 to the 6th, 10 to the 7th, so on and so forth. Okay. So I do this for population, prison, homelessness numbers for the same reason that population has these really large outliers. The number of incarcerated folks in different states also has these few values which are extremely large, because you can imagine it's related to population. Homelessness is the same thing. Then I actually construct the rates, the incarceration rates and the homelessness rates by dividing the raw numbers by the population in each state. Okay. So I'm also going to do a little bit of just exploratory data analysis, looking through, before I start building the models, just looking through some plots to see if I can identify trends in between the variables. So what I'm going to do here, actually, just let me produce the plot, and then I'll talk through it. I must have missed defining one of these here. Let me try this again. Okay, yeah, so I must have just missed executing one of these. So what I'm doing here is I'm plotting, I'll pop this legend on. So I'm plotting the log base 10 of number of incarcerated by log base 10 number of homeless. Okay, so it's my X and Y. Then I'm coloring by population. What this coloring does is it's a nice way to visualize three variables on a single plot. So I have X, Y, and then the coloring gives me a third variable. Okay, and so we have a trend here where the yellow points are higher population states, the red points are lower population states. And so I'm looking for any trends between colors or trends between X and Y. So we can see that as X increases, the color gets lighter, right? So the number of folks in prison in each state goes up as the population of the state goes up, right? And that's pretty intuitive. But sort of surprisingly is what's going on the y-axis. We see that as the number of homeless people in each state goes up, the population is not necessarily, it's not trending more yellow when we go in this direction, right? So that's sort of, at least with these points in here, so in these points, maybe you could say they get more yellow, but the trend is not as strong as it is with the the number of people in prison in each state. And so just the code that does that, again, I'll post this so you can look at it in detail, but what I do is I define some colors. That is, I take the colors between red and yellow and I divide them, and I have these color increments. So I step between red and yellow, where the number of increments I take between red and yellow is the length of this vector. Then I assign colors according to the ranking of the population. Okay, and then when I add this additional color argument, I include that ranking. Okay, because this is geographical data, I'm going to make some fancier plots. This is sort of context dependent, but if you do have data where geography is natural, you can use things like geographic plots. So here I've used the US map package to plot population. Okay, so here we have the shading according to the population, and again the log scale makes it so that there's not just one extremely large population and all of the other ones are washed out. Doing the same for prison, number of people in prison by state. So here we see that, so comparing it to population, Texas is a little bit lighter than California, but when we plotted the prison numbers, Texas is perhaps even darker, or at least as dark as California. Okay, so this suggests that maybe relative to the number of people in the state, that Texas has a higher incarceration rate. Homelessness numbers, California very high. Michigan here is also darker. Okay. So yeah, so just looking at trends. This is again just part of the exploratory data analysis, trying to familiarize myself a little bit with the data themselves before I try and build some models. Okay, so I'm going to produce some of the same plots looking at rates of homelessness and incarceration. So here, once we've accounted for the number of people in each state, so we're looking at number of incarcerated individuals in each state. Here, Alaska is darker, right? So I guess relative to its population, Alaska has a higher incarceration rate. Homelessness homelessness rates, right? So this is number of homeless per person in the state. Here we see something unusual, and this is Michigan's numbers. So Michigan's numbers 0.12. So this is approximately 1 in 10 people in the state is homeless. I've never been to Michigan. I have no idea. I suspect this is a data entry error. But this is what the data are telling me. So, yeah, I don't know what's going on in Michigan. If I take the log, so let me just show this plot and describe what I'm doing here. So if I look at this plot, right, Michigan is washing out all of the other states. I have a single extremely large value. All these other values are so small relative to this large value, it's hard for me to actually see what's going on in the rest of the image. And so by taking a log of this, of homeless per capita, I'm going to reduce that right tail, and I can hopefully then interpret the numbers on a log 10 scale and see something more meaningful. So that's what I see here. So this is log 10 of homelessness rates. Okay, so this -1 is 10 to the -1, which is approximately 1 in 10. That's that Michigan number. But we can see the shading where, you know, California corresponding to, I don't know, I can't really tell so well, perhaps 10 to the -3. So that's 1 in 1,000 people in the state is homeless. But yeah, so you can see more meaningful information, right? Okay, some of the plots we've seen before, a pairs plot. So here I have the kernel density estimators along the diagonal here of each of the variables, correlation here on the off diagonal between this is incarceration rates and homelessness rates, and then a scatter plot down here. Here again we have Michigan really throwing off the plot. It's hard to interpret what's going on because Michigan's homelessness rates are so high. A correlation plot telling me exactly what I have seen in that correlation number, but just visually. So here I've removed Michigan. Same plot, just removed Michigan. The idea being that, well, it makes it hard to visualize, right? So my scatter plot is much more meaningful. My kernel density estimator of the homelessness per population is much more meaningful. Still, we have this strong right tail even after we remove Michigan. Okay. So I'm going to try homelessness per population with the log transform just to see if it will make that kernel density estimator a little less skewed to the right, and indeed it does. Okay. So again, this is just, for me, this is heuristic. There's no mathematical reason why we would prefer a predictor with this eliminating this strong right skew, but I've seen that this works better in practice, that if you eliminate this strong right skew, try and get something that looks more like a normal distribution, oftentimes this will help. We've also talked about looking at residuals, right, as one way to identify if you need transformations. That is the mathematical way to motivate it, but oftentimes reducing your strong skews is just good practice. Okay. All right. Again, so this is the exact same plot we just looked at. So, actually no, this is so what I'm doing here is I've included here I'm plotting against log homelessness per population. So instead of homelessness per population, this is on the log scale again, where homelessness per population is interpreted as 10 to the negative 2 is 10 to the, or negative 2 here is 10 to the negative 2 homelessness rate. And what that does is that reduces some of the right skew again. But in general, I see that the relationship between homelessness rates and incarceration rates doesn't seem to be doing much, right? Maybe there's a slight negative trend here where more incarcerated means lower homelessness rates, but there doesn't seem to be any strong trend between the two of them. That's supported by this correlation number as well. So that's the quantitative predictors that I have. I talked about how I'm going to introduce the qualitative or the categorical predictors as well. And so what I'm going to do is I'm going to use state level predictors. So that is, each state is going to be given a contrast. Okay. So the way that I do that in R is I can just use this categorical predictor, which is the abbreviation, right? The CA for California, as a predictor. When I build a linear model like that, I see the following. Okay, so each of my categories has a coefficient, right? These are contrasts. We don't call them slopes because slope sort of implies a continuous change in x, gives a continuous change in y according to the slope. So we call them contrasts instead. Here I see contrasts for all these different states. And one obvious question here is, what is my reference category, right? What is my reference category here? These are, of course, adjusted effects, i.e. contrasts. So what is my reference category? And it is Alaska. So Alaska is AK abbreviation, and it's not shown here, even though it was in the abbreviation column, because it was the first in the column alphabetically. R automatically made that my reference column, and so then each of these contrasts are to be interpreted in context of adjusting the log of the homelessness rates according to these numbers here. Okay, so you would say California, the log homelessness rate in California relative to Alaska, you would subtract 0.15. Okay, if I want to set the reference category manually, I mentioned this in the slides, but if I want to do that, then I can explicitly set the reference category with relevel here. So relevel setting my reference to California. Then when I look at my coefficients here, I have no California listed because it's my reference. Alaska is listed, and so then all of these contrasts are being interpreted relative to the reference category. right? And this is actually kind of interesting. So I will say one of the best examples that I've seen of the usage of the reference category uh, in this class is I had a student do a project looking at predicting vehicle prices based on different attributes of the vehicle. And what they did, quite cleverly actually, is they used their reference category was like a, I don't know, like a 2006 Toyota Camry or something, and it plugged in all the attributes of a Toyota Camry and used this as its reference as a reference category, because everybody has in their mind when you describe a vehicle, okay, Toyota Camry, sort of like four-cylinder sedan, kind of boring car from the perspective of it's not like doesn't have extremely high gas mileage or anything dramatic, right? And so by using the Toyota Camry as a reference category, you could look at the contrast and say, okay, how are we adjusting vehicle price? For example, adding more cylinders or making a two-door instead of four-door, yada yada yada. All these different categories, we can interpret them relative to how would we adjust relative to a Camry, and I think it was a powerful way to incorporate the reference category and make your interpretation easier. So let's continue plotting along here. I will say that actually using states as predictors is not a very good idea because there's one observation for each state, right? So when I'm using this as a predictor, I'm definitely overtraining to this data set because each of my observations gets a contrast, right? So instead of predicting with state, I'm going to use the geographic region. This US map package in R that I've been using to make these plots defines regions. So they have a south region, they have a northeast region, so on and so forth. And so what I'm going to do is I'm going to use all these regions to define a new column. Okay, so define all these columns, set them to null, and then loop through the columns and say if the state is in these different regions, then set it equal to true. So this is I'm defining these true in R is treated as a 1 or a 0, so a binary predictor. True is a 1, false is a 0. So what I'm basically doing is I'm defining these binary columns according to is the state in these different regions. Okay, so that's what this for loop does. Basically says for each of the abbreviation or for each of the regions. For each of the rows, if the state is in the region, make the corresponding entry in the column true. Okay. So I've labeled all these regions. If I omit one as a predictor, so here I've omitted the western region, that's going to become my my reference category. Okay, so just looking at these. So here I have the intercept, which is the western region. So this is the prediction corresponding to the reference category. The southern region, the northeastern region, and the midwestern region. So these are all my contrasts. And then I'm going to do the same here where I include incarceration rate as a predictor. Okay, let me just go through and interpret these really quick, right? So this is saying that the log homelessness rates of the western region, my estimate is 10, almost 10 to the negative 3, so 10 to the negative 2.8 because I'm working on a log scale here. And then I would adjust, so the southern region has lower homelessness rates, the northeastern region has higher homelessness rates, and the Midwest has lower homelessness rates, right, relative to the western region, because that's how I interpret those contrasts. Here I'm going to include the next model. I'm going to include incarceration rates. Again, the idea being that I want to see if it's useful as a predictor, these there we go. All right, so these I can look at these coefficients, right? So here I have my reference category is Western, but I have a slope corresponding to this quantitative variable, and then these contrasts are for each category here. Okay. So interesting, right? Let's just talk this through a little more. So this was the model that I had when I didn't include the prison, and this was the model that I had where I did include the prison. And so we will notice what's happening is that once we account for incarceration rates, uh, the Midwestern adjustment, so knowing that we're in the Midwest region, this contrast gets much larger. Okay, so what that suggests is, so it's just an interesting relationship. Including this predictor makes this decrease, this contrast. Okay, and so let me think about actually how to interpret that. So this is saying that I guess in general, it looks to me like the incarceration rates in the Midwest are lower because once I know, wait, is lower the right direction? Let me see here. So yeah, so if the incarceration rates in the Midwest are a little bit higher, actually, right? Then to pull the back down to my original prediction, I would need a larger or a more negative contrast, right? So this is suggesting to me that the incarceration rates in the Midwest are actually higher than they might be elsewhere. But interesting, right? So the contrast can change with having new information, and this is just an example of that here. Okay, and then the last thing I'm going to do here is, well, one thing I can do, I'm not going to, but we've talked about this before. I can look at my residuals, iterate on my model, perhaps applying some transformation, looking at how my assumptions are satisfied. In general, my assumptions are satisfied here: the mean zero assumption, constant variance assumption, and normal residuals assumption. And this is something that can help me guide transformations, but because the emphasis is on these categorical predictors, I'm just going to say we can do that with this by plotting a linear model, but I'm not going to. The last thing I'm going to do is I'm actually going to see through some testing root mean squared error if the prison predictor is useful. Okay, so the way that I'm going to do that, I wrote a nifty little function. We have homelessness predicted from region and prison, or homelessness predicted from region. I have formulas for both of them. Okay. And then what I'm going to do is I'm going to build this function, and this function takes the formula, takes the data, takes the number of repetitions you want to make, and takes the name of the variable you want to predict. In our case, this is the log homelessness per population. And what it does is it performs however many reps you want, that number of trained test splits, and computes your testing RMSE, and then it will return to you the mean and the standard deviation of it will turn the root mean squared error for those however many repetitions you did, those trained test splits, right? So it's going to have a bunch of test RMSEs for a bunch of trained test splits, okay? And then what I did is I took those, for example, here I take 100 trained test splits. I have testing root mean squared errors for 100 trained test splits. I'm going to take the mean and take the standard deviation, and that will give me some idea of what's the typical test root mean squared error, and and how volatile is it. Okay. So when I do that, I have this is the test root mean squared error without prison. So this is the sample mean of those 100 repetitions and the sample standard deviation, and I'm going to do the same now with prison as a predictor. Okay, so I have a little bit higher test root mean squared error on average, and a little bit lower sample standard deviation. Okay, so based on this information, I mean, I added a new predictor, and the sample mean of my test root mean squared errors went up, right? So I could do just 3 trained test splits or however many I want. I just chose 100 because it's a nice even number. It's a little overkill because we only have 50 observations in this data set, but I just want to sort of illustrate the idea here of how you might automate taking some trained test splits. But in general, I would say that I'm not enthused about prison as a predictor, or the incarceration rates as a predictor, right? Because my test RMSE went up. So I have more information, yet my testing RMSE went up. So there's no reason for me to add this predictor to my model. Okay, so that's all I have to say about qualitative predictors. So again, this was sort of a little bit of a top-to-bottom data analysis, plus building some models and doing some EDA, things like this. So the takeaway is that we can use qualitative variables as predictors, and yeah, so I will see everybody next time.